Yeah. So I'll be sharing my screen. One of you can unmute and let me know if my screen is visible and if I'm audible. Okay. So can you guys see my screen? Can one of you unmute and let me know if my screen is visible and if I'm audible? Okay, okay. Thank you. Okay, great. So good evening, everyone. Today is the sixth live session of the series of live session, basically where we discuss some problems from this course, Fundamentals of Protein Chemistry, taken by course instructor Professor Dasgupta from IIT Kharagpur. So what we do is that basically in these live sessions we discuss some of the questions, some of the concepts behind those questions, and we not only discuss the answers to that particular question, but we try to discuss the concepts behind those questions so that similar type of other questions we can solve on our own, right? So that is the main purpose of these sessions. So, and we try to keep it as interactive as possible. So in case you have any questions or doubts, you can type in your chat box or raise a hand or maybe unmute and let me know. If I know the answer that time, I'll just tell you. If I don't, then you'll have to give me some time. I'll read and come back to you. Okay? So my name is Aishi and I'm a PMRF research scholar, PhD student from Department of Chemistry, IIT Bombay. So going to the first question for today. I think this we have already discussed. 1 second. We'll start today's session. I'll just let you know. This also we have discussed. Okay. So the first question for today is this. So you can see, based on the titration curve for arginine provided, the ionic structure expected at pH 13 would be what? So you have the image over here, you have all the options over here. I'll give you a few minutes. If you want, you can try and answer the questions. Then we'll move on to the discussion. Any of you? Anybody? You can try answering. I'll wait for a few minutes, then we can discuss. You can think about it at your own pace. Please, you can try. This is the titration curve for arginine. Arginine is a basic amino acid, we know that. So based on these informations, if you want to try, okay. So the answer will be, we'll discuss the question, then we'll come back to the answer, okay? So let's talk about the absorption of ultraviolet ray light by aromatic amino acids. We know that we can find out the concentration of proteins using UV as well. So tyrosine and tryptophan are significantly more polar than phenylalanine, these amino acids, because of the tyrosine hydroxyl group and the nitrogen of the tryptophan indole ring. Right? So tryptophan and tyrosine, and to a much lesser extent phenylalanine, absorb ultraviolet light. This accounts for the characteristic strong absorbance of light by most proteins at a wavelength up to 80 nanometer, and a property exploited by researchers in the characterization of proteins. So if you see this graph, x-axis we have wavelength, y-axis is absorbance, and it basically shows the absorption of ultraviolet light by aromatic amino acids, comparison of the light absorbed light absorption spectra of the aromatic amino acids tryptophan and tyrosine at pH 6. The amino acids are present in equimolar amounts and under identical conditions, and the measured absorbance of tryptophan is as much as 4 times that of tyrosine. So know that the maximum light absorption for both tryptophan and tyrosine occurs near a wavelength of 280 nanometer. So light absorption by the third aromatic acid phenylalanine, which is not shown in this image, generally contributes little to the spectroscopic properties of proteins. Okay. Now, the amino and the carboxyl groups of amino acids, along with the inositol R groups of some amino acids, function as weak acids and bases. So when an amino acid lacking an ionizable R group is dissolved in water at neutral pH, it exists in solution as a dipolar ion or zwitter ion, right? Which can act either as a base or as an acid. Now, substances having this dual or acid-base nature are known as amphoteric and are often called ampholites from amphoteric electrolytes. So, a simple monoamino or monocarboxylic amino acid such as alanine is a diprotic acid when fully protonated. It has two groups, the COH group and then the NH3. If you see the non-ionic and zwitterionic forms of amino acids, these are the non-ionic form does not occur in significant amounts in aqueous solutions. Zwitterion predominant at neutral pH. A zwitterion can act as either an acid or a base. Okay. So it exists largely in neutral deuteronic form, as I said, influenced by the nature of the side chain. And amino acids exist as a zwitterion, which is basically having a formal positive and a formal negative charge. So the overall charge is neutral. Now, amino acids are amphoteric. They can react as either an acid or a base. And ammonium ions acts as an acid, the carboxylate as a base. So now what is isoelectric pi? We have also pH. We have discussed this as well. The pH at which the amino acid does not have any net charge. And in case of electrophoresis, separation of solar polar compounds based on their mobility through solid support, and the separation is based on charge or the molecular mass. Now, if you see this titration curve is of an amino acid, here the titration curve of 0.1 molar glycine, and when you have degrees Celsius, ionic species predominating at key points in the titration are shown above the graph. The shaded box is centered at about 2.K1, 2.034 and pKa2, including the indicate the regions with the greatest buffering power, right? So this is what tells us about the buffering power. Now note that the one equivalent of OH minus or the molar like 0.1 molar NaOH is added. Okay. So this is the titration curve of, I think, alanine. So if you see the pKa1 carboxylic acid is 2, the pKa2 amino group is 10, Pi is pK1 plus pKa2 by 2. So at isoelectric point, the pH at which the number of positive and negative charges on a population of molecules is equal. This is ionic atoms forms of alanine in acidic, neutral and basic solutions. If you can see, alanine in acidic solution is pH less than 2, net charge will be plus 1, right? Whereas alanine in neutral solution is pH approximately 6 and net charge will be 0. That's an isoelectric form because no net charge, so it's an isoelectric zwitterionic form. Whereas in case of alanine in basic solution, pH greater than 10, net charge will be minus 1. This is the titration curve for glutamic acid. pKa1 is 2.2, pKa PK2R group is 4.3, PK3 amino group is 9.7. So the PI will be PK1 plus PK2 by 2, which is 3.25. It's a titration curve for lysine. PK1 carboxylic acid is 2.2, PKA amino group is 9, PK3R group is 10.5, and PI will be PKA1 plus PKA2 by 2. Now, pKs of charged amino acids are groups: aspartate, glutamate, histidine, cysteine, tyrosine, leucine, arginine. Right, so they have their own pKa values. Now we turn to polymers of amino acids, the peptides and proteins. The biologically occurring polypeptides range in size, being from small to very large, consisting of 2 or 3 or 1,000 of linked amino acid residues. So our focus is on the fundamental chemical processes of these polymers. Now, peptides are basically nothing but chains of amino acids. So two amino acids metabolite molecules can be covalently joined through a substituted amide linkage termed a peptide bond to avail a dipeptide. Such a linkage is formed by removal of the elements of water, dehydration from the carboxyl group of one amino acid and the amino group of another. A peptide bond formation is an example of a condensation reaction, a common class of reactions in living cells under standard biochemical conditions. The equilibrium for the reason favors the amino acids over the dipeptide. To make the reaction thermodynamically more favorable, the carboxyl group must be chemically modified or activated so that the hydroxyl group can be more readily eliminated. We see the formation of peptide bond by condensation. The amino group of one amino acid with R2 groups act as a nucleophile to discuss the hydroxyl group of another amino acid with R1 group, forming a peptide bond. Three amino acids can be joined by two peptide bonds to form a tripeptide. Similarly, 4 amino acids can be linked to form tetrapeptides, 5 to form pentapeptides, and so on and so forth. This is joined, the product is called polypeptide. The proteins may have thousands of amino acids residues. Although terms protein and polypeptide are sometimes used interchangeably, molecules referred to as polypeptides generally have molecular weight below 10,000, and these called proteins have higher molecular weights. Now, in a peptide, the amino acid residue at the end with a free amino group is the amino terminal or the N terminus, and the residue at which at the other end where carboxyl group is free, it's called a C terminal. So when an amino acid, because of a polypeptide, peptide and protein left, display the amino terminal end is right on the left and the carboxyl terminal end to the right. So see this red, left to right, beginning with the amino terminal end. So if you see this figure, the pentapeptide here, peptides are named beginning with the same amino terminal residue, which by convention is being placed at the left, and the peptide bonds are shadowed in light red and are groups in red. So, what are the properties of a peptide bond? It's a rigid covalent bond and has partial double bond character. It's thinner and unrotatable. The peptide bonds generally in the trans conformation septate bond is able to form maximum two hydrogen beads with her polar body. The other polar atoms basically. A peptide bond formation is reversible. A peptide bond can be broken by the hydrolysis, the addition of water. Enzymes such as pepsin and trypsin digest hydrolyze proteins to free amino acids during the digestion. However, to break peptides free of non-enzymatically requires harsh conditions like 6 molar HCl and 24 molars. 24 hours. So the product of the polycondensation of a different number of alpha amino acids bound by the peptide bond are known as peptides. It contains two amino acids known as dipeptide and join containing three amino acids is a tripeptide. One containing a large number but less than 3D less than 50 amino acids a peptide. So one containing 50 to 100 amino acids polypeptide. And if the number of the amino acids is higher than 100, the polysaccharide is called protein. Now, biologically active peptides and polypeptides occur in a vast range of strengths and compositions. So, no generalizations can be made about the molecular weights in relation to their functions. Naturally, the occurring peptide range is between 2 to many thousands of amino acids. Even the smallest people can have bear me can have biologically important effects. Consider the commercially synthesized dipeptide L-aspartyl, L-phenylalanine, and methyl. Natural sweet sweetener better known as aspartame as artificial sweet, and peptides exert their effects on very low concentrations. For example, a number of variable hormones, number of vertebrate hormones, it's called peptides, is included in the oxygen and gland, and which stimulates uterine secretions, contractions. And thyrotropin releasing factor 3 residues, which is basically found in the back of hypothalamus, and it stimulates the release of another hormone, thyrotropin, from the anterior pituitary gland. Some chemistry, some extremely toxic mushrooms positions such as amanitin are also small peptides as a many antibiotics. So, what is the biological activity of peptides? Glutathione's has antioxidant in plants, animals, and fungi, bacteria, and it is capable of preventing damage to important cellular components caused by reactive open series such as the free radicals peroxides. Now, oxytocin and vasopressin are non-peptide hormones containing 9 amino acids released by the pituitary pituitary. Now, oxytocin is released into the bloodstream as a hormone in labor, as it plays in birth, bonding with the baby and the milk production. Vasopressin helps water resorption by the renal tubules. Cord. Now, some proteins consist of a single polypeptide chain, but others contain multi-subunit proteins have two or more peptides associated with one acid non-covalently. The individual polystyrene chains in the multi-subunit protein may be identical or different. So, if at least two are identical, the protein is said to be oligomeric, and the identical units are referred to as protomers. Hemoglobin, for example, has four polypeptide subunits, two identical alpha and two identical beta chains. All four get held together by non-covalent interactions. So each in an identical way within a beta subunit within structure of his multi-subunit protein, so that hemoglobin can consider either a tetramer or a dimer. So we can calculate the approximate number of amino acid residues in a single person related to the mass. Now, if we talk about the stability and the formation of liposomes, hydroxypeptide bond favor energy critically, but an uncatalyzed reaction is very slow. And strong mineral acids such as 6 molar HCl good quality for hydrolysis, and amino acids must be activated by ATP driven reaction to incorporate. If we talk about enzymatic and chemical cleavage of peptide linkage, you can see the source of all these amino acids on the left hand image. This is a titration curve of tetrapeptide. So coming back to the question that we started with, if we talk about the question that we started with over here, so basically in here, arginine has three ionizable groups: alpha carboxyl group pK 2.17, alpha amino group of pK 9.04. This pK refers to the protonated form NH3 plus, and guanidinium side chain pK 12.48. A rule of thumb from the Henderson-Hasselbalch is if pH is greater than pK, the deprotonated form dominates. If pH is less than pKa, the protonated form dominates. Now you compute these values in the equation, and basically it gives out the answer 3. Okay. So the correct ionic format page 13 is the one showing carboxyl HCO minus, neutral H2 on the alpha carbon, neutral guanidine side chain. That is option A. The other choices are wrong because they show groups that are still protonated, which are inconsistent with pH 13 being greater than the 11 pK values. Okay. Any doubts? Anyone? If you have any question, you can talk to me now, and we'll wait for some few minutes, then we'll move on to the next question for today. Any query? Otherwise, we'll move on to the next question in a few minutes. Okay, I'll wait for a few more minutes. If you don't have any doubts, we'll move on to the next question for today. So we on to the next question. Okay, so the correct order of energy for the electronic transition is this. These are the four options. Which one do you think is the correct among these? Anybody? I'll wait for a few minutes. You can think about the answer. We'll discuss electronic spectroscopy clearly. Let me know if you can answer the question, then we'll move on to the theory part. Anybody? You know about electron spectroscopy? You can try about these answering this question about electronic transition. Okay, so let's discuss about electronic spectroscopy. So, if you know ultraviolet and visible spectroscopy, this is the earliest method of molecular spectroscopy and phenomenon of interaction of molecules with UV and visible lights. Now, absorption of motor photon results in electronic transition of a molecule, and electrons are promoted from ground state to higher electronic states, right? Right. So now, in structure determination, UV-based spectroscopy is used to detect the presence of chromophores like dienes, aromatics, polyenes, and conjugated ketones. Right. Also, it's very useful in quantitative analysis of compounds with chromophores. If you think about chiroptical spectroscopy, optical rotary dispersion, ORD, and circular dichroism, CD. The difference in the refraction or absorption of left and right circular polarized light is measured. Absorptivity between left and right circularly polarized light. Now, what is chiroptical spectroscopy? It basically reflects stereochemical arrangement of atom in a molecule. Both CD and ORD show sense of handedness in reflecting the handedness of the non-superimposable mirror image molecule in enantiomer, right? So the curves appear as positive or negative peaks of cotton pegs, reflecting the difference in the chirality of molecule. How do you display the spectra? The horizontal scale is all three methods will use lambda in nanometer unit. Vertical scale will be ordinate, UV vis absorbance or molecular absorptivity or epsilon. Now CD difference in molar absorptivity. Uh, Delta epsilon is molar delta epsilon and theta is molar ellipticity. And then we have molar rotation as well. These are some. So if you see over here, absorbance versus wavelength. Okay, for different isomers, they have tried to plot it, as you can see from this image. Now, what is the origin of this electronic spectra? Absorptions of UV vis light photons by molecule results in electronic excitation of molecule with chromophore. Right? So, the electronic transition involves promotion of electron from the electronic ground state to a higher energy state, usually from a molecular orbital called HOMO to LUMO. Now, HOMO is the highest occupied molecular orbital and LUMO is the lowest unoccupied molecular orbital. Electronic transition usually originates from valence electrons in a chromophore, such as the non-bonding or pi electrons in unsaturated functions. If you talk about electronic transition, can be assigned to different transition types according to the molecular orbital involved, such as pi to pi star in alkenes or benzene, N to pi star in keto group. Due to the symmetry property in molecular orbitals, such transition can be allowed high intensity or forbidden low intensity. So absorptions with high epsilon are allowed transitions and low epsilon absorptions are forbidden transitions. Then we have the UV spectral origin, transition of an electron from HOMO to LUMO by light photon. Now UV absorption for some isolate chromophores is here. You can see the table and the list over here. Now how do you do the measurement of UV absorptions? The electromagnetic radiation may be described by the wavelength lambda, it is a nanometer, by the frequency or by the wave number related by energy difference as the following relationships. We know all the relationships. The UV region is divided into two parts. The near UV region 190 to 400 nanometer and the far or the vacuum UV region below 190 nanometer. So the far UV region has interference due to the absorption of oxygen, which must be removed or flushed with the nitrogen in the spectrometer to obtain the spectra of sample. Now the absorbance or molar absorptivity of an UV band is calculated according to the Beer-Booger-Lambert law. Okay, so I naught is the intensity of incident light, I the intensity of transmitted light, the path length in centimeter, and the concentration in mole per liter, K is absorption coefficient, and molar extinction coefficient or molar absorptivity, centimeter square, mole per mole, and all of that. Now the relationship between K and epsilon is, since absorption is this, log I naught by I. So the actual quantity measured will be the molar absorptive intensity of the light beam transmitted by a reference cell containing pure solvent and an identical cell containing the sample solution. Okay, so this is a measurement of solute absorbance by a double beam spectrophotometer. Now, what is the Frank-Condon principles? The broadened bands of UV curve indicate wide distribution of energies due to superimposition of several vibrational levels on the electronic level. Okay, so is it transitions between the lowest vibrational state in ground state to various vibrations in the excited state that determine the shape and the intensity of a UV band. So it is determined by the spacing of the vibrational levels and the distribution and contribution of each vibrational subband to the total band intensity. It is governed by the Frank-Condon principle, stated as nuclear motion is much slower as compared with electronic motion in transition, so it is negligible during the time required for electronic excitation. Since the nucleus does not move during the excitation, the internuclear distance keeps the same, and the most probable component of an electronic transition involves only the vertical transitions. Okay. Now, what are the solvent effects? Promotion of electron from ground state to electronic state leads to more polar excited state that is more easily stabilized by polar solvent associations. Or edge bonds. So, in going from non-polar to polar solvents, the fine dibronic structure is smoothed into a broad band. So, for pi to pi star transition, the pi star state is more polar and stabilized more in polar solvent relative to the non-polar one. Thus, in going from non-polar to polar solvent, there is a red shift or bathochromic shift. Now, for N to pi star transition, the end state is much more easily stabilized by polar solvent effects. So, in going from non-polar to polar solvent, there is a blue shift or hypsochromic shift. Okay, as you can see. So, if you can see, we have UV absorption spectra for methyl 3-pentene 2-one in left methanol and right heptane. The spectra in methanol were run in 1 centimeter cuvette. Spectra in heptane were run, and you can see the vertical axis is in the absorbance units. So we have discussed about the solvent effect as well. Now if we talk about electronic transition measures the probability and energy of exciting a molecule from ground state to excited state or promoting electron from HOMO to LUMO. For each energy state, both singlet and triplet states are possible. In singlet state, the spins of electron pair are antiparallel. If the spins are parallel, three states are possible and are jointly called the triplet state. Okay. Selection rules allow S to S and T to T processes that not singlet to triplet and triplet to singlet. So ground states are usually singlets, thus most excitations are to singlet excited states like S0 to S1, S0 to S2 and all of that. Triplet states are usually formed by the intersystem crossing from an excited singlet state such as S1 rather than by the direct excitation from the S0 ground state. Now, the electronically excited states may decay unimolecularly back to the ground state by photophysically emitting energy of fluorescence from an excited singlet state or of phosphorescence from an excited triplet state. So, alternatively, it may decay photochemically to a different ground state of different structure. So, one can measure that. Thus measure the absorbance and emission from molecules, and the lambda max of absorption band correspond to the excitation energy, and E max, epsilon max, to the intensity of transition, a measure of the probability of promoting an electron given the excitation energy, right? So you can see these are the electronic transitions we have been talking about. Electronic activation and decay mode of a chromophore. You can see from S0 to S2 and then from S0 to S, that is absorption. Fluorescence will be S1 to ground state, and intersystem crossing is S1 to T1 and T1 to S0, which is a very rare process, is called phosphorescence. Now, the wavelength of an electronic transition depends on the energy difference between the ground state and the excited state. It is useful approximation to consider the lambda to be determined by the delta E of the MO originally occupied by the is at the GS and the higher excited molecular orbital in electronic excited state. So the order here is sigma, pi, n, pi star and sigma star. Okay. If we talk about the different types of UV transitions, relative electronic orbital energies and selected transitions in order of increasing energy. If you can see in the diagram over here. Now UV transition type 1 is like sigma to sigma star transitions for CPDs with sigma bond only. Okay, appears in saturated hydrocarbons with sigma orbital and transition to antibonding sigma star or to molecular Rydberg orbital. Okay, then N2 pi star transition, the excitation of an electron on a non-bonding orbital such as the unshared pair electrons on oxygen, nitrogen, sulfur to an antibonding pi star, usually in a double bond with heteroatoms such as C double bond O, C double bond S, in double bond O, etc. And then we have the pi to pi star transitions for containing double, triple bonds or aromatic rings. Pi electron is excited to an antibonding pi star orbital, and this is usually a sim allowed and high energy transition. Then we have ethylene absorbs at 162 nanometer in vacuum UV Extended conjugation lowers delta E and increase in lambda max if extended beyond 5 double bonds and getting into the visible region. Okay. Then you have the N2 sigma star transitions, excitation from non-bonding orbital to an anti-bonding sigma star orbital. Okay. And then there's something called the Rydberg transition, which is basically to mainly to high excited states for most organic molecules occurs at lambda below 200 nanometer. It's a part of a series of molecular electronic transitions occurs with narrowing spacing nearing the ionization potential of organic molecule. Okay. So we have discussed all of these. Now if you talk about the orbital spin and E states, there is a diagram showing the ground state and excited state configuration of carbonyl chromophore. Singlet state have electron spin paired and triplet state have two spins parallel. So n orbital containing two electrons is perpendicular to pi star orbitals. You can see. Now what are the terms that we use while describing UV absorption? So chromophores, these are functional groups that give electronic transitions. Oxochromes, which are substituents with unshared pair of electrons like OH, NH, SH. When attached to pi chromophore, they generally move the absorption max to a longer wavelength. Then we have the bathochromic shift to longer wavelength, also called red shift. We have the hypsochromic shift to shorter wavelength, called the blue shift. We have the hyperchromism, increase in epsilon of a band, and we have the hypochromism, decrease in the epsilon of a band. Okay, namely the orbital spin states. Now, singlet state is most molecules have ground state with all electrons spin paired, and most electron states also have electron spin all paired, even though they may be one electron each lying in two different orbitals. So such states have zeros total spin and spin multiplicities of 1 and are called singlet states. Okay. Total spin will be plus half minus half, so 0. Now if an external magnetic field is applied to the singlet spin system, there is only one zero angular momentum in the field direction. Okay. So for some of the excited states, there are states with the pair of electrons having their spins parallel. In two orbitals, leading to total spin of 1 and multiplicities of 3. Orbitals for triplet state, under the influence of external field, there are 3 values, like 3 energy states of 1, plus 1, 0 and minus 1. So the angular momentum such states are called triplet states. And according to the selection rule, S to S, T to T are allowed transitions, but S to T and T to S are forbidden transitions. Like singlet to triplet and triplet to singlet are forbidden transitions. Okay. Now, electronic transitions may be classed as intense or weak according to the magnitude of epsilon max that corresponds to the allowed or forbidden transitions as governed by the following selection rules or electronic transitions. So, what is the spin selection rule? There should be no change in spin orientation or no spin inversion during these transitions. So thus S to S, singlet to singlet, triplet to triplet allowed, but singlet to triplet and triplet to singlet are forbidden and not allowed. And you have the angular momentum rule. The change in angular momentum should be within 1 unit. And you have the symmetry rule. The product of the electrical dipole vector and the group theoretical representations of the two states is totally symmetric. Now, the spin selection rule simply states the transitions between states of different multiplicities are forbidden. Okay. Now, the selection rules of electron transition, the second rule agrees with the fact that most states are within 1 unit of angular momentum of each other, and the symmetry rule indicates that group representation of initial and final states should be the same as the representations of axis systems they belong to. So they are different, then the transition moment of that transition is 0 and the transition is thereby forbidden. So group representation is the symmetry property of the orbitals. Now what are allowed and forbidden transitions? Forbidden transition is the N to pi star transition of saturated ketones where a carbonyl N electron is promoted to an orthogonal pi star orbital and there is no orbital overlap for such 90-degree movement of charge and the transition moment is 0. Allowed transition will be the for pi to pi star transition in double bond and the symmetry of initial and final states are the same and a large transition moment occurs to give high intensity of the band. Now for forbidden transitions, the N to pi star transition of keto group is still observable with low intensity. This is due to the vibronic states in the transition. Symmetry of orbital changed by C double bond O vibration that allows some overlap of orbital and the transition to occur. A shape of electronic absorption band arises from various vibronic sublevels. So the band intensity is described by epsilon max in UV and this quantity cannot be calculated theoretically but can be calculated by the wavelength weighted area under the absorption band. So in UV curve it is called the dipole strength or D. You can see how D is calculated over here as well. So dipole strength represents electronic transition probability of the absorption band and as electron is promoted from low to high energy states, a momentary electric dipole is generated called the electric transition dipole moment mu, which is related to D by D is, you can see it is a dot product of mu. So dipole strength is the following equation relations calculate D in terms of lambda delta lambda. Now the absorption spectroscopy basically provides information about presence or absence of unsaturated functional groups useful adjunct to IR infrared determination of concentration, especially in chromatography for structure proof, usually not critical data but essential for further studies. NMR, MS, not very good for purity though. So, our transition from a lower level to a higher level with transfer of energy from the radiation field to an absorber atom molecular solid. Emission is basically transition from higher level to a lower level with transfer of energy from emitter to the radiation field, but no radiation is emitted. transition from higher to lower energy levels is called non-radiative decay. Okay, so nuclear motion is negligible during the time required for an electronic excitation, and since the nuclei do not move during the excitation, the internuclear distances remain constant, and the most probable component of an electronic transition involves only the vertical transition. Now, origin of electronic spectra. So, absorption of UV vis photons by molecule results in electronic excitation of molecules with chromophore. Chromophore is any group of atoms that absorbs light whether or not a color is thereby produced. Now, the electronic transition involves promotion of electron from an electronic ground state to a higher energy state, usually from a molecular orbital called HOMO to LUMO. So you have the biological chromophores, the peptide bonds and amino acids in proteins. The p electrons of the peptide group are delocalized over the carbon, nitrogen and the oxygen atoms. The N to pi transition is typically observed at 210 to 20 nanometer, while the main pi to pi transition occurs at 190 nanometer. Aromatic side chains contribute to the absorption at pi greater than 230 nanometer, and purine and pyrimidine bases in nucleic acids and their derivatives, highly conjugated double bond systems. All of these. So selection rules, we have talked about these. No need to get into too much details. These are all what we have already talked about. Electronic transitions, we have talked about the electronic transitions, the different bands. The bathochromic shift is basically a shift to longer lambda or lower energy. Histochromic shift is blue shift to shorter lambda, higher energy. Hypochromic effect is an increase in intensity. Hypochromic is a decrease in intensity max. Okay, that is how this works. I'm not going into more details. So coming back to the question that we started with, basically. Okay, wait. So properties of molecules will always depend on the specific kind of atoms they are composed of. That is true. The special structure of the molecules, the way in which the atoms are arranged within the molecules. So the binding energy of atoms or atomic groups in the molecule. Now the monoatomic molecules, the elements that do not have tendency to form molecules, the elements which are stable single atom molecules are the noble gases, such as helium, neon, argon, krypton, xenon and radon. Diatomic molecules are composed of only two atoms of the same or different elements like hydrogen, oxygen, carbon monoxide and nitrogen oxide. While polyatomic molecules consist of a stable system comprising three or more atoms. Okay. So, if you talk about the empirical formula, it indicates the simplest whole number ratio of all the atoms in a molecule. Molecular formula describes the exact number and type of atoms in a single molecule of a compound. Structural formula indicates not only the number of atoms but also their arrangement in space. If we talk about isotope, atoms with the same number of protons but different number of neutrons are called isotopes. By changing the number of neutrons, isotopes still maintain the same overall neutrality and hence the chemical behavior remains unchanged. Okay, if we talk about isomers, it's two molecules with the same atoms joined together in a different shape. They have same molecular formula but different chemical structure. For example, butane and isobutane, right? Same molecular formula and everything, but the way they are attached to the main atom is different. Then we have allotrope, which are different structural forms of the same element but can exhibit quite different physical and chemical properties. For example, carbon, diamond, graphite. These are nothing but allotropes. Structural isomers will be same molecular formula but different structural formula. Allotropes like diamond and graphite are two allotropes of carbon, pure forms of the same element but different structure. Now, molecular spectroscopy is basically the study of the interaction of electromagnetic radiation with matter. So, based on the analysis of EM radiation that is emitted, absorbed, or scattered by molecules, we can have information on chemical analysis, molecular structure like bond lengths, angles, strengths, energy levels, etc. Now, a quantum mechanical system or particle that is bound, that is confined spatially, can only take on certain discrete values of energy called energy levels. And the term is commonly used for the energy levels of electrons in atoms, ions, or molecules, which are bound by the electric field of the nucleus. Can also refer to the energy levels of nuclei or vibrational or rotational energy levels in molecules. Okay. Now, if an atom or ion or molecule is at the lowest possible energy level, it and its electrons are said to be in the ground state. If it is at a higher energy level, it is said to be at the excited, or any electrons that have higher energy than the ground state are excited. If more than one quantum mechanical state is at the same level, energy levels are called the degenerate energy levels. Now, chemical bonds between atoms in a molecule form because they make the situations more stable for the involved atoms. Covalent bonds involve the sharing of electron pairs between atoms. As atoms approach each other to a covalently bond, their orbitals affect each other's energy levels to form bonding and anti-bonding. Molecular orbitals. The energy level of the bonding orbitals is lower and the energy level of the anti-bonding orbitals is higher. For the bond in the molecule to be stable, the covalent bonding electrons occupy the lower energy bonding orbital, right? Which may be signified by such symbols as of pi or sigma. Now, orbitals of individual atoms interact to produce new orbitals called the molecular orbital. So, if you can see, this is the molecular orbital sign, and in molecules of discrete energy levels, no continuum between levels. Okay, so it absorbs electromagnetic radiation when the energy of photon corresponds to the difference in energy between the two states. And energy can be stored either as potential energy or kinetic energy in a variety of ways, including translational energy. Small amounts of energy stored as kinetic energy, or rotational energy. Kinetic energy associated with the rotational motion of molecules. Then we have vibrational energy, the oscillatory motion of atoms or groups of atoms within a molecule. Potential energy, kinetic energy exchange. Then we have electronic energy, energy stored as potential energy in excited electronic configurations. All except translational energy are quantized. Okay. So when an atom or molecule in an excited state falls to a lower energy level, it emits a photon. And molecules typically remain excited for a few nanoseconds. Upon excitation, emit a photon of light. This process is called fluorescence. So atoms and molecules can also absorb photons, making a transition from a lower level to an excited state. We've gone through this. Visible light can also be absorbed by electron transitions. Higher energies are absorbed more relative to lower energies. Red light is less strongly absorbed than blue light. So absorption of visible light causes heating but not exactly ionization. So like car windshields transmit visible light but absorb higher UV frequencies. The energy level of infrared light corresponds to the energy required to cause molecular vibrations, which arise as molecular bonds are not rigid but behave like springs. So, vibrational transitions can be subdivided into two classes: stretching, which can be either symmetric stretching or asymmetric stretching, and then bending, like scissoring, rocking, wagging, and twisting. So stretching frequencies are higher than corresponding bending frequencies. So it's basically easier to bend a bond than to stretch or compress it. Bonds to hydrogen have higher stretching frequencies than those to heavier atoms. So triple bonds have higher stretching frequencies than corresponding double bonds, which in turn have higher frequencies than single bonds. So, like quantum energy of microwave photons matches the ranges of energy separating quantum states of molecular rotations. So, like electronic and vibrational transitions, a rotational motion of molecules is quantized. So, absorption of microwave radiation causes heating due to increased molecular rotational activity. So most matter transfer into mu waves. Microwave ovens use high intensity U waves to heat material. Okay. So we'll not go into too much detail. Coming to the question that we started with. So the question that we started with was the correct order of the energy for the electronic transitions, and the answer will be this. So does anybody have any questions related to this? We will stop for a few minutes and then we'll resume. If you have any questions, you can ask, or we'll stop and then we'll go back to the next question. questions? Anybody, any questions? If not, we'll move on to the next question for today. Okay, so moving on to the next question for today. Which among the following amino acids has the highest molar extinction coefficient? A, B, C, D. These are the four options you have. I'll wait for a few minutes. You can try answering the question. Anyone? Can't argue with it. Okay, so we'll start discussing this. The correct answer is C. Why we'll discuss. So first we'll talk about photometry, estimation of analyte concentration on the basis of light absorption, right? So photometry is basically one of the most widely used analytical procedures in biochemistry for simple routine determination of small quantities of materials. The principle is based on physical laws of radiant energy and light, right? So basic photometry principle can be applied in several analytical procedures like measurement of absorbed or transmitted light, colorimeter, spectrophotometry, atomic absorption, turbidometry, measurement of emitted light, film emission, photometry, fluidometry, etc. Now, these are optical instruments, spectrophotometers, for measurement of the absorption of a light of a given wavelength, right, of colored substances in solution. Now, Beer's law makes it possible to calculate the concentration of the colored substance in the solution. Now, absorption photometers for work in aqueous solution work in the ultraviolet and visible ranges from wavelength around 240 nanometer up to 750 nanometer. And the principle of spectrophotometers and filter photometers is that monochromatic light is allowed to pass through a container or cell with optically flat windows containing the solution. Now it then reaches a light detector that measures the intensity of the light compared to the intensity after passing through an identical cell with the same solvent but without the colored substance. From the ratio between the light intensities, knowing the capacity of the colored substance to absorb light, it is possible to calculate the concentration of the substrate using Beer's law. So in spectrophotometers, a monochromator with prism or with grating is used to obtain the monochromatic light of one defined wavelength. So this is the spectrophotometer schematic. If you see, you have the source, then you have the entrance slit. You have the dispersion device, exit slit, sample and detector. If we talk about Beer's law and spectrophotometry, it relates the concentration of the optical measurement of absorbance combined with spectrophotometry can be used to distinguish and compare different molecules in solution. So light of a particular wavelength enters the sample, light scatters through particles in solution and reducing light transmission. Light is absorbed by molecules, particles and emitted at different wavelengths, reducing light transmission. Absorptivity is usually specified only at lambda max, which is the wavelength at which light is most strongly absorbed by the light absorbing species. So it's proportional to concentration. Then we have Beer's law. Okay. Now the Beer-Lambert law states that there is a linear relationship between the concentration of a solution and the absorbance of the same solution. For a spectrophotometer, the direct proportionality between absorbance and concentration must be established. So, a calibration constant may be derived and used to calculate the concentration of an unknown solution by comparing with a calibrating solution. So, you will need blank, a standard solution, calibration curve, and all of that. At first, a standard curve or a calibration curve is prepared, which is usually made using a series of standard solutions, known concentrations, and measured using a spectrophotometer instrument to determine the unknown concentration of sample. It's represent a graph where the concentration is plotted against absorbance. Then a straight line is fit to the data that you obtain and the resulting equation is used to convert the absorbance of the unknown sample into concentration. So the equation of this line by first finding this and changing into this y equal to mx plus c, which is the equation of a straight line. So for this experiment, the slope and intercept of the line provides a relationship between the absorbance and the concentration that determines the Beer's law. Now, Lambert-Beer law is used to determine the concentration from absorbance if the molar extension coefficient of a compound and the path length of the cuvette that the distance light passes through solution are known. The formula for this relationship is this: E equal to ELC. Okay, according to the Lambert-Beer law, an increase in the concentration of a solution leads to an increase in the absorbance as linear. To plot any data in Excel, you should enter the data, create a scatter plot with only markers from data, and then add linear regression or add trend line to make Excel the better line fit to the data, and can be used as a formula y equal to mx plus c to calculate the concentration of the unknown compound, right? This is how the thing is done in Excel. But nowadays there are always better advanced software such as Origin or GraphPad Prism. So how to make a standard curve? Basically, multiple samples with known properties are measured and graphed, which then allows the same properties to be determined for unknown samples by interpolation on the graph. The samples with known properties are the standards and the graph is the standard curve. So you can draw the points with protein concentrations as x values and the average absorbance as y values on a grid or graph paper. Draw straight lines to the points. Look up the unknown protein concentrations from the plot using the absorbance value of the unknown protein. Like this. Okay. This is an experiment. We are now going to get into the experiment. Now, amino acids, if you talk, you know about the different structures of the amino acids, right? Cysteine and the disulfide bonds, polar uncharged side chains, polar charged side chains, and all of that. We know about pK and pi. Pi is the isoelectric point, pH at which a molecule carries no net electric charge, and all of that. We know about if we can draw polypeptide, how a peptide bond looks basically. It links one amino acid to another, torsion angle in proteins. Peptides typically assume the trans conformation. We know sequence, so we know about the sequence coils in right-handed manner. Hydrogen bonding along the helical axis from carbonyl oxygen of residue N to the amino hydrogen of residue N plus 4. Hydrogen bonding stabilizes the alpha helical structure. Then if you can notice the hydrogen bonding from the carbonyl oxygen to the amino hydrogen. Then protein purification overview. First we do extraction, then we capture, then intermediate purification, polishing, and all of that. We are not getting into. So what is the molar concentration of a solution? If you see, so for suppose you have a protein mixture, you need to determine the protein concentration. You cannot use the Beer's law because you would not know the extinction coefficient for the protein mixture at 280 nanometer. So what is the alternative approach then? Bradford protein assay. So how does Bradford protein assay work? Basically, it's a reagent that contains humousy brilliant blue, which reacts with basic, especially like arginine and aromatic amino acids to yield a blue color with a density proportional to the protein concentration. Right? So if you have to create a series of protein standards at known increasing concentrations and mix with the Bradford reagent. And you have to treat the protein mixture of unknown concentration also in the same way as the standards and compared visually the spectrophotometrically. Like this. Okay. So we have talked about proteins, we have tripeptides, polypeptides, which are chain synthesized based on the specific bodily DNA, amino acids, all of that. Structural differences between carbohydrates, lipids, and proteins. Now, the anatomy of the amino acid, something we have been reiterating since the first class. The amino acid structure has the side chain, the amino group, the acid group. Okay, like we have glycine, aspartic acid, like phenylalanine, different amino acids showing their unique side chains. Now, from when the acid group of one amino acid joins with the main group of a second amino acid, formed through condensation, broken through hydrolysis. Essential, non-essential, and conditional. Essential must be consumed in the diet, non-essential can be synthesized in the body, and all of that. structure of the protein, denaturing. Okay, this is a quick review. Will not get too much into this. These are, I'll be uploading all the slides. These are some manual photos that I have taken just to make you conversant to the topic. So coming back to the question that we started with, which among the following amino acids has the highest polar extinction coefficient? Phenyl, phenol, indole, and imidazole. Right? Like if the R group is phenyl, like the side chain is phenyl, R group is phenol, R group is indole, or the R group is imidazole. So if we think about it from the perspective of what we have learned over here right now, okay, so if you think like that, we have to recall the essential relevant amino acids. For the phenyl group, we have phenylalanine. For the phenol group, we have tyrosine. For the indole group, we have tryptophan. For the imidazole group, we have histidine, right? So, if you see, the highest extinction coefficient is of tryptophan, which is an indole group. Okay, so indole has the highest, tryptophan has the highest extinction coefficient, then phenol, then phenyl, then imidazole. Okay, so if you want to answer, if you want to know why is it so, why indole absorbs so strongly compared to phenol and phenyl in terms of conjugation and transition. So basically the basic principle is absorbance depends on conjugation plus allowed transitions. So the molar extinction coefficient epsilon at a given lambda, like for example 280 nanometer, is directly related to the probability of an electronic transition. So the more delocalized pi electrons a chromophore has, and the more the transition asymmetry allowed, the stronger the absorbance, like larger epsilon. So if you compare the four groups, phenylalanine, side chain is simple benzene like phenyl ring. Benzene is pi to pi star transitions absorbed near 260 nanometer but with low intensity at 280 nanometer. Conjugation is limited. Result is a weak absorbance. For tyrosine with the phenol side chain, phenol ring, the OH group donates electrons by resonance into the ring, increasing the conjugation and altering the transition probability. This shift absorbance into the near UV and strengthens intensity. The result is moderate absorbance. For tryptophan with an indole ring, the side chain is an indole ring fused benzene plus pyrrole. So highly extended conjugated pi system, electrons in 10 pi electrons in aromaticity plus extra from pyrrole. Pi to pi star transitions are strongly allowed and overlap well with the 280 nanometer, and this makes tryptophan's absorbance dominant in proteins, even if there is only one tryptophan versus many tyrosine phenylalanine. The result is very strong absorbance. Then we come to histidine, which is an imidazole, side chain imidazole, 5-membered aromatic with 6 pi electrons. Conjugation is smaller compared to indole. The pi to pi star transitions are weak at 280 nanometer. The result is epsilon is less than 100 per mole per centimeter, negligible absorbance. So phenylalanine will have weak absorbance because of little conjugation. Tyrosine will have stronger absorbance because of phenolic resonance. Tryptophan or indole will have the strongest extended conjugation, high transition probability, while as histidine, which is imidazole, weakest, small ring pore overlap at 280 nanometer. That's why in protein concentration assays at 280 nanometer, the signal is mostly dominated by tryptophan, with a smaller contribution from tyrosine and a negligible one from phenylalanine and histidine. Okay, so that is the answer to this question. Any doubts? If you have any doubts, you can ask me now. Okay, so if nobody has any query on this question, then we'll stop the session here today and we'll meet again next week, same time. So otherwise I'll be uploading all these videos on YouTube and all the slides will also be uploaded. Okay. Anybody? Yes. Hello? I cannot hear you. Can you type? I cannot hear you. Are you saying something? Can you type it out? I cannot hear you at the. Your voice is cracking. Okay. Thanks. We can stop the session now and we'll meet next week. Thanks.